streets, I'm a mobster. You got 50 whole bed, you'll be my sponsor. Them snakes on the plane, me and Kanye Conda. Yeah.
Hi guys, my name is Nako Nakatsuka. I'm a 4th year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So the next topic we wanted to cover is resonance. So basically what resonance is a way of describing delocalized electrons, which are electrons that are not associated with a single atom or covalent bond. And so let me write this in note form for you. So it describes delocalized electrons, which again, electrons that are not associated with single atoms or covalent bonds within certain molecules where bonding cannot be expressed by one single Lewis formula. So, Lewis formula, not enough. So instead, resonance structures are represented by several contributing structures, and this is what resonance structures are. So instead, explained by several contributing structures. So basically, several Lewis structures are used collectively to describe actual molecular structures, which is the approximate intermediate between the canonical forms. And thus we get something called a resonance hybrid. But before I get into all of those nitty-gritty details, let me show you this picture of the carbonate ion. So carbonate is CO3 2-, and these are the different structures of carbonate. If you see this, you can see that it basically has resonance because these three structures right here differ only in the positions of the electrons and not in nuclei. And thus they are not isomers, they are not anything that involves different positioning of nuclei. It is solely based on the position of electrons. So now let's look at the first structure right here. So we have a double bond up here and single bonds for these two oxygens. So now if you use the formal charge equation, which I hope you've seen from your general chemistry classes, right here, you can calculate the formal charge on any atom. So as an example, I can show you how to calculate the formal charge of this oxygen right here. So this oxygen with just one single bond has a valence of 6 electrons, right? The total number of non-bonding electrons are 2, 4, 6 electrons, minus the total number of bonding electrons divided by 2. There's 2 in this bond right here, and so it's 2 divided by 2, and we end up with -1. So this oxygen has a formal charge of -1. It's the exact same formal charge for this oxygen, and now let's try for this double bonded oxygen. And this is a carbonyl, if you remember all the different functional groups we talked about before. And so in this case, so let me draw this out right here, is C single bond O is -1. And now if we look at C double bond O, the valence is going to be 6 again. The number of non-bonding electrons is 1, 2, 3, 4. And the number of bonding electrons is 4 as well in this double bond. And so it's 4 divided by 2. And we end up with 0. So the formal charge of this particular oxygen is 0, and that's why the overall charge of this carbonate ion is 2-, which is contributing from these two single bonded oxygens. But in this case, this structure has a resonance form, the reason for that being this double bond. This double bond can be moved or shifted to a different location, such as here, where it went from being here to over here. So now, instead of this guy having a formal charge of 0, this oxygen that's double bonded has a formal charge of 0. This, in turn, has -1 and -1. Finally, the final resonance structure that this can have is this double bond right here. So basically, since there's 3 positions in which the double bond can move, this carbonate ion has 3 resonance structures. And these structures, again, differ only in the positions of the electrons and not the nuclei, since they all look the same. From here, we can draw this structure, which is often called the composite or the resonance hybrid. And in this case, as you can see, these dotted lines indicate that the double bond can be in each of these different locations. The reason why the charge right here is negative 2/3 is because each contributing bond is a result of the average of the formal charge. So since we have -1 times 2, right? Because we have CO single bonds, we have 2 of those guys, and just 1 double CO bond. And so the total of this ends up being -2. And since we have 3 bonds, we have to divide that charge by 3. And that's where we get this charge on each of the atoms for the resonance hybrid. And the overall charge on the molecule still remains as being 2-. Although I just introduced you to the whole concept of resonance, let's pull it back a notch and let me introduce to you how we even came up with the concept of the resonance hybrid. So when we talk about single, double, and triple bonds, you know by now that they have different lengths and different strengths, right? So going from a single bond to a double bond and then finally to a triple bond, it gets shorter. And also, when you go from a single to a triple bond, it gets stronger. This makes the triple bond much harder to break, or you need more energy to break the bond in comparison to a single bond. But you know this already. So, in theory, if I drew out this nitrate ion, which is NO3-, and I just drew it out like this, which is one of the resonance structures, if the theory of the whole single, double, and triple bond having different lengths and different strengths is correct, the nitrate ion would have one bond that's shorter and stronger than the other two, right? Since this nitrogen and oxygen bond is a double bond, this, in theory, should be shorter and stronger in comparison to these single bonds between the nitrogen and the oxygen. However, this is not the case. When we took this and analyzed it in a lab, we found out that all 3 bonds of nitrate have the same strength and length. So all 3 bonds have same strength and length. So something must be going on, because based upon our understanding of the length of the bond and the strength, this molecule should not be symmetric. So now we have to think about what is going on, and the lab analysis also showed us that the actual bond length between each of these atoms is longer than a double bond but shorter than a single bond, and weaker than a double bond but stronger than a single bond. So basically there's this intermediate bond thing going on. So thus, from here, they concluded that the molecules resonate between 2 or more different structures. And so from here, they came up with this hypothetical switching from one structure to another, which they call resonance, because each of these bonds are symmetric, but they're in the middle between a single and a double bond. And that's why we can come up with this resonance hybrid structure, which has single bonds and double bonds depending on which resonance structure it takes on. And so in this case, it's just the same as the carbonate ion that I showed before. This is going to be -2/3, -2/3, and -2/3. But as you can see, each of these bonds have the same contribution. So another thing that's very important to understand is, why is resonance so important? Why do we even care? Well, resonance delocalization increases the stability of a molecule. So the first point I wanted to talk about was that resonance increases stability. So when electrons or charge, which is negative because they're electrons, is spread over a larger volume, you increase the stability of that particular molecule. So this is a result of charge distribution over larger volume. The second point I wanted to mention was that resonance highly influences molecular structure. So resonance influences molecular structure. And I already talked about how important molecular structures are in the previous chapter. And this in turn also causes planarity. So as an example, I wanted to show you the reaction between sulfuric acid and water. So if I start out with H2SO4, and I'm going to draw it like so. And we add an OH minus ion to it. We end up with this structure, where this is now O minus instead of OH, where this H joins the OH minus to create water. So this looks like a very straightforward acid-base reaction, right? Well, look at this molecule right here. This has resonance, right? This has resonance because there's a single bond right here, there's a negative charge, a formal charge on the oxygen, and there's two double bonds right here. So basically, this molecule can have charge moved to different points in the molecule. And so since this has resonance, it's more stable. On the other hand, this OH minus molecule has no resonance. And neither does this molecule. And thus, it's less stable. Because of this, the equilibrium constant is greater than 1. What does this mean? Well, if you remember learning about equilibrium, it's the concentration of the products over the concentration of the reactants, right? Well, we're going to end up with more product because it's the more stable molecule. So if you have more of the product, you're going to have a larger K equilibrium value, and thus it's going to be greater than 1. And that's why H2SO4, sulfuric acid, is a stronger acid than water, because of the fact that without its resonance, it's less stable, whereas in this case, it has resonance and it's a stable molecule.
Yeah, overseas nigga, top flow, clear windows nigga, glass house.